Hello, hello. I am Samson Rainey from AGU's press office, and without further ado, I will say, welcome to Space Helicopters, Aircraft for Other Worlds, originally scheduled for 9 a.m. Central. Thank you for making it for this revised time. A reminder that the roundtable titled Arrival Preview, NASA's first asteroid sample return mission, will follow at 3 p.m. across the hall in N231. After our presentations here, we'll take Q&A in the room and online. Please first state your name and your media affiliation. If you're online, you can either type your question in the Q&A box or request to be unmuted. And without further ado, we will begin. Håvard, I believe you are first up.
All right. My name is Håvard Grip. I'm the aerodynamics and flight control lead and the chief pilot for the Ingenuity Mars Helicopter. So I am here to talk to you about Ingenuity. There we go. This is Ingenuity, the first aircraft in history to operate from the surface of another planet. We originally sent Ingenuity to Mars as a so-called technology demonstration. Basically, we wanted to fly on Mars in order to prove that it's possible to fly on Mars. But Ingenuity over the past couple of years has had a phenomenal run and has far exceeded those original objectives. And I want to take you through some of the milestones along the way. There we go. Ingenuity left our planet and headed out into the solar system in July of 2020. At the time, it was a passenger on the Perseverance rover, which was headed to Jezero Crater in order to search for signs of past life. That journey through space lasted about 7 months. And in February of 2021, Perseverance descended to the surface of Mars, carrying Ingenuity underneath its belly inside a protective cover. Once we were safely on the surface, our first job was to find a place to put Ingenuity down on the surface. So we spent a few weeks staring at rocks and ripples on the surface, looking for that perfect spot. And when we finally found it, we sat for days biting our nails here on Earth and watching Ingenuity deploy through a sequence of steps that ended with Ingenuity finally sitting on the ground and feeling the Martian dirt underneath its landing gear for the first time. 2 weeks later came our big moment. It was time to try for the first time to actually fly on Mars. And we were scared to death. Sitting on the ground, waiting for those first bits to trickle down from Mars after that first flight, because failing when we'd come that far was just something we didn't really even want to contemplate. And thankfully, we didn't have to, because Ingenuity did a perfect job flying that first flight, as you can see in this footage that was taken by the Perseverance rover. It did such a good job, in fact, that even though we originally were meant to fly only up to 5 times on Mars, we got a new mission, which was to use our unique aerial vantage point to act as a reconnaissance platform for the overall mission. And the flight that I'm probably most proud of in that respect is our flight number 13, where we went to this beautiful outcrop called Feu, and we took images of it from multiple different angles in order to build a 3D model of it that scientists could then use and investigate. After this scouting mission, followed a grueling trek across an area called Zeta, which was very treacherous terrain. It took several months. And we finally made it out of there with a record-breaking flight, our flight number 25, which measured more than 2,300 feet in distance. So it's the longest flight to date. Right on the heels of that, we went scouting again, this time not for science though, but for engineering purposes. We went and had a look at the parachute and back shell from Perseverance's landing on Mars. And this is quite valuable for the people who built that system, because they actually get to see what their hardware looks like after having gone through that violent event of entering into Mars's atmosphere. Final milestone I want to mention is just a few days ago, we for the first time flew with a new set of capabilities. We gave Ingenuity an upgrade, a flight software upgrade. It can now navigate more accurately than ever before, and it can also use its cameras on board to look for hazards when it's landing. You can see how that works in this video, which is based on a previous flight, where the hazardous rocks are marked in red and candidate landing sites are marked with a green cross. So then what is next for Ingenuity? Ingenuity right now is stationed at the foot of an ancient river delta in Jezero Crater. You can see an image of it here. And our plan is to use these new capabilities that I just talked about to head into those hills together with Perseverance. And that will be by far the most challenging undertaking that we've ever attempted with Ingenuity. So before I hand things over here, I just want to show you one thing, which is this book. This book is called The Nominal Pilot's Logbook for Planets and Moons. And we made this shortly before landing on Mars. And of course, we were only ever going to fly 5 times with Ingenuity. But we thought, well, a book with only 5 pages, it's just going to look too silly. And so we put a bunch of extra pages in here just so it would look more like a real book. But guess what? We are out of pages as of 2 days ago. Ingenuity made its 36th flight. We have 36 pages in here. And coincidentally, that also marked the threshold for Ingenuity having spent a full hour in the skies of Mars. So with that, I'll hand it over to Teddy, who's going to be talking about the next generation of helicopters to fly on Mars.
Thank you, Håvard. Good afternoon, everybody. So, yeah, we've had a whirlwind last year and a half flying the baby on the surface of Mars. My name is Teddy Tzanetos. I'm the Ingenuity team lead, but also the new rotorcraft mission at Mars, the Sample Retrieval Helicopters manager. I can't express to you how happy the Ingenuity team is that we've been able to demonstrate all that we have, the opportunity that we've had to learn. But the most impactful lesson learned that we're carrying forward is really the reason why we can talk about what comes next here. So we've been flying for a year and a half. We've learned how to fly reliably now at Mars. And about 6 months ago, the next campaign to Mars Sample Return, came to our team and asked, clearly Ingenuity's design is robust, clearly it's reliable, and we've learned a lot. Could it be possible that we could pick up a sample tube? Our team had been working on this idea as a concept in the months prior, a research study to look into the feasibility of the underlying physics of the problem. Can we generate additional mass? Could we actually pick up a tube and reliably transport it around on the surface, right? Going from what we had, which was a technology demonstration, to now something that was serving a mission function, which was a big step for us all. And what we're looking at here is one of our first renderings of what we're imagining the next generation of Martian flight will look like. On the left-hand side, you have our Ingenuity Mars Helicopter on the surface of Mars. And on the right-hand side, you have her new younger sister, right, which is a similar rotorcraft, coaxial in nature. And you can clearly see the similarities in the design. 2 counter-rotating rotor systems, a solar panel up top, still self-sufficient from an energy perspective. But the key differences are the blaring ones, right? We have an arm now, and we have 4 wheels on each leg. Those new additions, those new capabilities are what allow this new mission component of the sample return lander element of MSR to pick up sample tubes one at a time and ferry them between a cache depot site here in Three Forks in Jezero Crater, around where Perseverance is today, to the eventual future landing site of the SRL lander itself. Now, this effort, SRH, is being designed as a backup. The primary method by which we will get our precious sample tubes from Perseverance to the lander and back to Earth is going to be a direct transfer from Perseverance directly to the lander. In the event that there's an issue from now until 2030 with Perseverance, the SRH helicopters, the two of them, will serve as a backup to provide that transport capability to go from a cache to the lander and still get these precious few pounds of Mars rocks back to Earth. Here you can see some of the technical comparisons between the two generations of rotorcraft. On the left-hand side, you see Ingenuity statistics, and on the right, we see SRH's initial design points here. So we want to, where we can, rely on heritage, and where appropriate, deviate from that heritage to generate this new capability. But we are largely leveraging all the amazing lessons learned that we have learned and will continue to learn with Ingenuity over the last year and a half. Here we see our 4-sol cadence that we're baselining for SRH. Each of the 4 sols will have a unique focus. Sol number 1, we will fly from the Mars lander to a small landing site near the cache depot. Sol 2 will pick up a tube, from the surface. Sol 3 will fly back up to 700 meters away. We'll fly back to the lander. And Sol 4 will do the precision approach, where we will drive from the landing pads near the lander up until the workspace of the arm and deploy a sample tube. At that point, the next helicopter could go out and retrieve another sample in parallel, so that we can, as efficiently as possible, get these samples from the regolith on Mars back onto our equipment on the lander and ready to return back to Earth. Here's an early prototype that our partners at AeroVironment built to help understand what a roving helicopter might look like, right? We're really a fusion now of a small little rover that can fly, or you can think about it as a small helicopter that can drive, right? We're combining a lot of what JPL and NASA has been really good at for the last couple of decades, but constraining it into a very, very lightweight vehicle. And that's not all. We're also dreaming up even further into the future here. Over the last 5 years or so, even before Ingenuity had its first flight, we've been scratching, a couple different concepts in the back of our heads here, thinking, what could scientists do with this new capability, right? If Ingenuity were successful and we had this new capability, what might a room full of scientists be interested in actually accomplishing on the surface of Mars and in the skies of Mars? And what we're looking at is Mars Science Helicopter. It's a research concept, imagining a much larger system on the scale of the rover itself. So this is a SUV scale multicopter, 6 rotors that can carry payloads in the 2 to 5 kilograms. So science payloads, 2 to 5 kilos, with an all-up mass around 30 to 35 kilos. And here's an animation showing of what that future might look like in the skies of Mars, right? My personal dream is, one day we'll have astronauts at Mars and there'll be fleets of vehicles zipping around, helping the first humans there with simple and complicated tasks. But it all started with that first 39-second flight that we did about a year and a half ago. Here we see Mars Science Helicopter using its payloads in flight, flying up to areas that rovers can't get to, for example, like cliff wall faces, flying down into lava tubes. You can imagine the access element of really utilizing that aerial aspect will hopefully open up a lot of science capability or science options for scientists in the years ahead of us. We can fly to biologically sensitive areas that we don't want rovers going to and disturbing, for example, and really just broadening that horizon. Here we see a lava tube con-op, for example. And for those of you familiar with Star Wars, there's obviously some good parallels there. Now, Mars Science Helicopter would definitely leverage a lot of the autonomy that we're trying to develop still today with Ingenuity and with SRH. All of our current concept of operations rely on direct communications to a landed element, whereas SRH, like Dragonfly, would be able to communicate, either to orbit or back to Earth directly. And with that, I think I'll hand it off to Zvi.
Thank you. Thank you. I'm Zibby Turtle at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, and I'm the principal investigator of the Dragonfly New Frontiers mission to Saturn's moon Titan. So we are planning to expand the use of robotic flight to planetary exploration in the outer solar system. That is timed right. So Dragonfly is in its preliminary design phase. We are working toward a launch date in 2027 and arrival at Titan by 2034. The reasons we want to go to Titan, there are a number of reasons we want to go to Titan. So it's an unusual moon. It's the only moon in our solar system with an atmosphere. But out in the outer solar system, the surface temperature at Titan is 94 Kelvin. That's negative 290 Fahrenheit. And at these temperatures, of course, like most of the moons in the outer solar system, the crust is made of water ice. And the atmosphere at Titan is made mostly of nitrogen, but the next major constituent is methane. And what you see here in the little animation graphic here is that the methane in Titan's atmosphere plays the role that water does here on Earth. So there are methane clouds, there's methane rain, methane lakes, rivers, seas. And so even though Titan has very different materials, the terrain on Titan is exceedingly Earth-like. It's very familiar. We have a lot of similar landscapes on Titan, including dunes, as well as the aforementioned lakes, rivers, and seas. So, so the other thing that methane does in Titan's atmosphere is at the top of the atmosphere, it breaks down and recombines to form very complex carbon molecules. So we have a very carbon-rich environment. This material falls out of the atmosphere. It mantles the surface of Titan, but Titan is an icy moon. And so there has been the opportunity in the past for this complex carbon-rich material to mix with liquid water at Titan's surface. There's also liquid water in the interior ocean deep within Titan, but we've had the opportunity for the water and organic material to mix at Titan's surface in the past. And this is what makes Titan so compelling to explore, because this allows us to understand how far organic synthesis can progress in an environment that has all of the ingredients we know to be necessary for life as we know it. So Titan gives us the opportunity to look for answers to questions like, what makes a world habitable? What are the chemical processes that ultimately led to the development of life here on Earth? And even has life developed elsewhere in our solar system? Although at 94 Kelvin, life as we know it certainly isn't going to be terribly comfortable. And fundamentally, Dragonfly is a chemistry mission. Titan has been doing the kind of chemistry experiments we can't do here on Earth because we don't have millions of years in the laboratory to do them. So Titan's been doing these for us, and Dragonfly is designed to pick up the results of those experiments. The other benefit of Titan's atmosphere is that physically, Titan is the easiest place in the solar system to fly from place to place. And that's why Dragonfly is designed as an X8 octocopter. This allows us to make these chemical measurements in different environments on the surface of Titan. There we go. And before I go further, just to talk about the size of Dragonfly, we've been talking about Ingenuity. Dragonfly is the size of the Perseverance rover. So that gives you a sense of how much physically easier it is to fly on Titan. The gravity is 1/7 that of the Earth. The atmospheric pressure is 1.5 times the atmospheric pressure here. So physically, it's just easier for heavier than air flight at Titan than it is even here at Earth. So the rotors on Dragonfly are about the same size as the Ingenuity rotors, about 1 meter. But we're flying around a lander that's the size of Perseverance. And with this, we carry our entire payload from place to place. We can make measurements, of course, on the surface as well as in flight. But at Titan, we don't have a fleet of orbiters, sadly, yet. We don't have a fleet of orbiters, so Dragonfly does direct to Earth communication from the surface of Titan. So you can see the high gain antenna there in its deployed position. Of course, we stow that to flight to be as aerodynamic as possible. We also actually use the same power source as Perseverance, the MMRTG, the multi-mission radioisotope thermoelectric generator. And the payload is shown here. We have a mass spectrometer. This is fed by a drill, the rotary percussive drill. Breaks up the surface. We can use pneumatic transport because we've got this great atmosphere at Titan to bring the material into the mass spectrometer where we can measure the details of the chemical composition. We can also measure the bulk elemental composition of the surface with a gamma ray and neutron spectrometer. And then we have a geophysics and meteorology package, a suite of sensors, including a seismometer to listen for Titan quakes. And of course, we have a suite of cameras to study the terrain around us and to do aerial imagery. So Dragonfly needs to fly completely autonomously. Of course, the light time to Titan is 70 to 90 minutes. So we will not be flying Dragonfly in real time from Earth. And so we have been doing in our preliminary design phase a lot of testing of different components of the mission, including the flight algorithms. And so we actually have footage here from testing out in Imperial Dunes near the California-Arizona border, in an area with terrain, with dune-like terrain, well, dune terrain, which is like that we will be flying over on Titan. And we're using this to test our autonomous takeoff, in-flight navigation, and landing algorithms. We've also been taking advantage of wind tunnel facilities here on Earth to do testing of our rotors. This is the Transonic Dynamics tunnel at Langley. And we were just there this fall doing tests of the dual rotor configuration. You can see there in this fantastic facility. And then we have a couple of chambers at APL as well. So this is the APL built Titan pressure environment chamber. You can see it off on the right of the image on the left here. This is our small chamber, and the team here is the team that's building the drill. You can see the drill on the right there, getting ready to sample water ice. This is at Titan temperatures. And then they ran this test multiple times looking at the sampling, and on the right you can see the mock-up of the sample container that's been designed for the mass spectrometer, and they're acquiring, once the drill gets down into the ice, you can see that chamber fill up with ice chips. So demonstrating the technology to do the sampling at Titan conditions. And then the other chamber that we're in the process of building here at APL. This is our large chamber. It's currently just called the Titan. This chamber is large enough that it will fit the entire lander, so that we'll be able to do thermal testing of the lander in its final configuration. So this is just in commissioning at this point, to be coming online soon for initial testing. So there's a lot of activity going on as we're in our preliminary design phase. Of course, we're looking forward in the long run to, like I said, take robotic exploration of the skies to Titan. Thank you.
Very cool stuff, Zibby. Thank you so much, panel. We're now going to open it up to questions from the media, both in the room as well as online. Please state your name and media affiliation before asking the question. Scanning the room.
Hi, Jonathan Amos from the BBC. God, I've got so many questions. Håvard, perhaps we could start with you. Can you talk us about flying into the hills? What sort of challenge that will represent, the sort of elevations that you're going to have to confront, and what that means for your mission? Because I mean, the Perseverance, as I understand it now, is going, after it's dropped the sample tubes in the next week or so, is then going to head back up over the Delta and beyond. And so you're going to go with it, yeah?
Yeah. So flying up these hills for Ingenuity is a challenge, in large part because of the way navigation works. We navigate by using camera to look down on the ground and seeing how that terrain moves relative to us. And then we combine that with some additional sensors, but that's a fundamental way that we can track our progress over the ground. And Ingenuity, up until this point, has always lived in the belief that Mars is completely flat, like a pancake. And it's only now with these most recent software updates that we're able to tell Ingenuity that no, in fact, it's not flat. There are hills here. And that changes how you interpret the terrain going past you. If you're looking at terrain going past you below and you interpret that with a reference that is flat, then you're going to draw sometimes slightly the wrong conclusions, and that's going to lead to navigation errors. This is going to be very helpful in that respect, this most recent update. It still is challenging because referencing that map and comparing to the terrain, it's, there's still potential for errors over time to grow there. And so there's still a challenge, but less so than it was before. The other thing is when we have flown Ingenuity up until now, it's been entirely on us on the ground to figure out where to send it. We have to use our eyeballs looking at satellite imagery to figure out landing sites. And we've been able to do that successfully so far, but it's going to get harder as we go up these hills because of the way the terrain is there. It's harder to correlate orbital imagery to small rocks on the ground. And so that's where this other feature comes in, where right before landing, it can take a look at the ground and figure out where the rocks are and avoid them. And so between those two features, we're hopeful that we're going to be successful in climbing up these hills. But it's definitely a challenge.
Is it one go? I mean, it's a 40-meter elevation, I think, from the crater floor to the top of the Delta.
Yeah, it
Go
varies.
stages
But,
all the way up.
But it's on the
You've
order.
never climbed more than 10 meters above the ground, have you? Right?
So Ingenuity always flies in a ground relative way. So we have a laser altimeter that we use to measure distance to the ground. We always try to keep that at a set distance. So even when we say, well, when you're flying at 10 meters above the ground, that's what we're doing all the way. So if we climb a hill, it's going to literally follow the profile of the hill and try to stay 10 meters above the ground.
I think we have a question online, Becca.
Yes, we have a question from Corey Powell reporting for the Wall Street Journal. If Perseverance stays healthy, is there a backup mission for the sample return helicopters?
No, right now the baseline mission is that the sample recovery helicopters are going to be there as a backup. We have been discussing using them to film the MAV launch, right, and deploying them from the lander top deck. But the core mission is to act as a backup for the sample tube retrieval element.
Any other questions in the room? Right, back to Jonathan Amos.
Zibi, a question for you. When they trialed Ingenuity on Earth, Håvard, correct me if I'm wrong about this, you had a tether, didn't you, holding Ingenuity or the engineering model to try and recreate the flight conditions that you would expect to meet on Mars. And I'm just wondering if you're going to try and do something similar or trying to do something similar to try and create the conditions of flying on Titan, because I think you learned a lot from doing that, right? Yes. I mean, some of you had to go manually of
Yeah.
trying to fly in those conditions, yes? And you
Yeah,
couldn't do it.
yeah, I guess answer my part of it. You're right. We did use a tether. So what we are able to do on Earth is in our facilities, we can recreate the Martian atmosphere, but for obvious reasons, we can't recreate the Martian gravity. And Ingenuity, it can lift itself in Martian gravity and Martian atmospheric conditions, but not if you throw Earth gravity in there. So we had to have a tether to partially offload Earth gravity, pulling basically on a fishing line on top of the vehicle. So that's what we did. So
Right, and so we have much the same challenge in that we can't replicate the Titan gravity and environment in a facility here on Earth. However, the scale of the Dragonfly lander, right? Ingenuity would fit on the table, so you can imagine the scale of the facility you need. Dragonfly would fit on this stage. And you saw the size of the chamber we're building to do the thermal testing, to build a chamber that would be able to replicate Titan at the scale we need to actually do flight testing would be prohibitive. So we are not going to be able to do the same kind of direct testing of Dragonfly, but we're using the facilities we have, for example, the TDT that can replicate the Reynolds number of the atmosphere that the blades will be experiencing to do all that testing and validate models of the flight of the rotorcraft. So we're using the facilities we have and the models we have to do that and mesh that all together.
And a quick one, Teddy, for you, the Mars Sample Return Helicopters, they've got the same wingspan, but they're heavier. I think, did I get that right? They're heavier. So you must realize that you have a lot of margin from Ingenuity to be able to do what you're about to do. Yeah.
Yeah, so a couple of notes on that, and Håvard, please feel free to jump in. The sample recovery helicopters, right now, with a sample tube, a filled sample tube, we're estimating the total mass to be on the order of 2.5 kilograms. Ingenuity, its all-up weight was 1.8. So that is a massive gulf in terms of thrust capability when we're talking about flying at Mars. There's two ways, or two things to consider when jumping up in mass. One is the thrust margin stance that we took with Ingenuity. As a technology demonstrator, we were conservative on our thrust margin because there were so many unknowns. Now we know a lot more. And the second element is in the drawing and in the table, yes, the rotors look the same, but we are exploring making tweaks to get the right balance of heritage versus new capability versus the right technical solution for the problem, right? At some point, you keep growing an aircraft and something needs to change to account for the new physical challenges, right? And we're doing testing. We've already done our first test campaign actually with SRH using old Ingenuity EM helicopters in our 25-foot space simulator. And we tried pushing the rotor system harder than we ever have in Ingenuity times to see, is there any margin left on the table, right? And we're going to keep testing that after the New Year's actually to see how much further can we push our old heritage design. And we're going to be making some very exciting, decisions in the months ahead of us here about how much of our heritage do we want to keep versus how much do we want to change? Like, for example, growing the rotor blades by 10 to 15% in diameter, right? If you do that, you're more efficient in terms of how much mass you want to carry and how much energy and power you need to expend to carry that mass. And that way, other elements of your design, like the battery pack, for example, won't be as heavily impacted.
We have another question online.
We have a question from Rebecca Sohn from space.com. Can you elaborate more on what you mean by not disturbing biologically sensitive environments on Mars? Do you mean areas that might have life? How might a helicopter do this?
Yeah, so in the concept video from Mars Science Helicopter, there are areas of interest that scientists have identified on Mars that, if we can avoid it, we'd rather not bring, man-made objects like a rover right over it. And in those areas, the concept here is that an aircraft could hover above it and perhaps, reach down with an ultra sterile arm and pick up a piece of sample from the surface. That way, we don't leave tread marks. We don't disturb the surface. We don't disturb it. Yes, from airflow standpoint, there will be some wind, of course, but that's very different than rover tracks driving along the ground on Mars.
This one's for ZB. I'm at the Dragonfly. Actually kind of dovetailing off what Jonathan was talking about a minute ago. When it comes to testing and designing something like Dragonfly, obviously for something for scaling something like that, when you've got a rotorcraft that, as you say, would take up that whole stage. Obviously there's a certain, I won't say diminishing returns, but it's kind of the same problem as the rocket equation. The larger you get, the larger you grow the rotorcraft, the more it needs to be, the more power it needs to have, and on and on and on. And obviously that sort of dovetails then into a question of, well, you know, the rotorcraft was designed to be able to take off and fly from place to place to accommodate finding new science at different sites in case one site wasn't that all that interesting, or just make sure you didn't have to have all your eggs in one basket, as I think one of the other folks on your team put it when I interviewed him recently. And how are you guys accommodating for that?
Right. So yeah, so it's a different kind of scenario than we're used to thinking about landing until Ingenuity really is the repeated landings, because absolutely with Dragonfly, the plan is to fly a few dozen times and explore a few dozen sites, because that way we can explore different terrain with very different geologic histories and see how the compositions vary from place to place. And so the design needs to be robust to, you know, the leg design, for example, needs to be robust to multiple landings. And that's something that that's actually received a lot of attention in our preliminary design phase to be able to make sure that we can land in different types of terrain and have the ability to land multiple times.
If I may, just one extra thing about that, because I remember, if I'm remembering correctly, when Huygens was designed to land on Titan, obviously almost 20 years ago now, it was designed with the intention in mind of possibly landing in liquids. So obviously there's a case of, well, this rotorcraft Dragonfly is going to be flying autonomously. Obviously there's some control you can have over where it lands. But what happens if it happens to land somewhere that you didn't want it to? Is there anything being taken into account with that? Or is that even something that needs to be taken into account, do you think?
It absolutely needs to be taken into account, right? And as you say, when Huygens was designed, we didn't know where liquids were on the surface of Titan, or whether there might be liquids. We suspected it, but at the time we didn't know. And so Huygens, in a feat of engineering that is quite impressive, was designed to be able to float and make measurements, scientific measurements of a liquid if it landed in a liquid, and to land on a solid surface and make scientific measurements on a solid surface, which is very impressive. We have the benefit for Dragonfly of 13 years of Cassini exploration in the Saturnian system, mapping Titan. We understand Titan's geology, its geography, its weather patterns. And so based on that, we know the terrain that we'll be landing in, and the initial landing site is within the dunes and interdunes near Titan's equator, and within 100 kilometers or so of an impact crater, an 80-kilometer diameter impact crater, which is gives us the opportunity to measure compositions in an area where we know the liquid water and organics may have had the opportunity to mix. But you're right, we are flying autonomously, and Dragonfly needs to be able to assess landing sites from a perspective of hazard avoidance. So we have a scanning LiDAR that continually tracks the ground to map the, to keep track of the nearest best landing sites in case of, a need to land quickly, as opposed to, completing the nominal flight pattern. The other thing that we need to be able to do with Dragonfly, or that we can do with Dragonfly because we fly, is scout ahead. Because we, again, don't have the benefit of the high-rise type data, tens of centimeter resolution imaging to plan out our traverses. And so with Dragonfly, what we can do is actually fly out, scout potential landing sites, come back to our previous landing site, which we know is safe to land at, and transmit the data to Earth and look at the potential landing sites, both from the perspective of a hazards and the scientific benefit. You know, is this an area we want to go? Is it like places we've seen before, et cetera? So we leverage the fact that we can fly to help with that hazard avoidance as well.
Thank you. Yep. I'm Nick Oakes from NASA Goddard, by the way. I interviewed Melissa Trainer, so.
Okay.
And we have a question online. I think we have time for a couple more questions.
Yeah, we have a question for Zivi from Corey Powell for the Wall Street Journal. On the issue of planetary protection, what precautions are you taking to prevent contamination on Titan? Or is the assumption that Earth life is not going to be an issue at 94 Kelvin?
Right. So the planetary protection protocols are designed to prevent the contamination of an environment that could support life, like a warm liquid water environment. The surface of Titan is certainly not conducive, and the ocean at Titan is very deep, unlike some of the other moons in the outer solar system. So Dragonfly and exploration of Titan has been designated at Category 2, planetary protection Category 2. We absolutely do need to pay attention to cleanliness. The tighter drivers for our requirements, however, are contamination control, because we don't want to get to Titan and make detailed compositional measurements of molecules that we brought with us from Earth. And so that's actually our tighter set of requirements, and those meet our planetary protection requirements as well.
Any other questions in the room? Any other questions online? All right, I think that's a wrap. Thank you, everyone.
Thank you.
Thank you.